Welcome to the R Lab for Chapter 8 on decision trees. In this video, we're going to look through methods for fitting classification trees and testing our classification trees in R. So the first thing we want to do is enter in our library, load our library. The library is called tree. If you don't have a library, you will get a yellow message across the top on in RStudio offering to install the tree or the package for you. If this tree library doesn't work, or it says it's not available for your version of R, try updating R. This tree package only works in recent versions of R. And then we want to use our library for our textbook, and we're going to attach the Carseats data. And so we want to use a classification tree to determine or predict whether these sales are going to be a high category or low category based on store location. And if we want to see what the Carseats data has in it, we can always do question mark and then the data set. And so these are sales of child car seats. And we see it's a simulated data set consisting of sales of car seats at 400 different stores. And we can go down the list here. It's sales at the store, price charged by a competitor at this location, community income at the location, local advertising budget for the company in this location, population, price, and so on. So we're going to create this variable that's called high. And if sales is greater than 8, this variable high gets a yes. If sales is less than or equal to 8, this variable gets a no. We do this using the if-else function in R. Now we're going to create a data frame combining the data frame for car seats together with this high variable. So now car seats has, let's just review here, 11 variables, and we're going to make this new data frame. And you can see up here now we have this data frame called car seats, and it has 400 observations and now has 12 variables because it has the high variable that we've added to it. And we're going to make a classification tree. And the notation or the syntax is similar to the LM linear model function or GLM generalized linear model function. We're going to predict high as a function of the dot means all variables, and then minus sales means except for sales. And we're going to use the car seats data here. And then we get a summary of this tree that we've created. So this gives us the call for the tree. This gives us the variables that were actually used. The tree has 27 nodes. This is residual mean deviance. It's similar to a Gini index. Not the same formula, but you can think about it a similar way. Lower is better. It's some measure of node purity. And then there's a misclassification error rate, which is 0.09 or 9% error rate. And that's on the training data. So we're going to want to do some better training and testing, something more rigorous or something proper than using the error rate on the training data. Remember, trees will tend to overtrain when they're first constructed if they're not pruned. And so we've created this tree, and now we can plot the tree. We can take a look at it. One of the nice things about trees is that they're easy to understand. You can plot them and take a look at them. So we see the first variable that's considered is shelf location. If the shelf location is bad or medium, you go down the left branch. If the shelf location is not bad or medium, which means it's good, that's the only other choice, you would go to the right branch. If we type the name of the tree in R, we get this information. So this is all the information that goes into or comes out of the process of building the tree. So each node is listed here. 1 corresponds to the root node, which has 400 variables. The first decision node is this node, which is written as a 2, and it's actually the outcome of this split on the left-hand side. So this is if shelf location bad or medium, right? So this is the yes side for this. If shelf location is bad or medium at this split, you go down that side, then this is the information for that side. So the meaning for each of those numbers is given up top here. The node number 2, the split is the split criteria. N tells you how many observations went down that branch or down that side of that split. So 315 observations went down this side of the branch. Deviance gives us this deviance value. The Y value here tells us the Y value or the output or the class label that goes with most commonly down this side, and so the most common Y value is node. And then these probabilities tell you the probability of having a no and then a probability of having a yes at this location. So your probability of having a no, if you go down the left branch here, is 68%. The probability of having a yes, meaning a high seller, is 31%. If we scroll down, we can find the right-hand branch at that location. It'll be number 3. Shelf location good, so that's the right-hand branch here. 85 observations went down there. Node purity was 90.33. Most common classification for things going on that side is a yes. Probability of being a no is 22%. Probability of being a yes is a 77%. So that's how we read all the information for our Carseats. Now we're going to do some splitting into training and test data, and then we're going to do some more rigorous evaluation on our test and training data. So we're going to set our seed so that we should get the same results every time you run or the textbook output runs. So we create our training data, and this is the sample command that we've used before. So it's going to give us a random sample from 1 through number of rows in Carseats. Remember, there's 400 rows, so this is 1 to 400. We're taking a random sample of that set of length 200. So this will give us, if we look over to train, it's a vector of length 200 containing integers, and there are the indexes for our training data. So now we're going to split out the training and test data. So Carseats.test is going to be the Carseats data without containing the train in it. So that's what we're going to use for testing. And then high.test is going to be that variable high, but without the training data. So that's going to be our test output, or the correct calls on our test data. So now we're going to train our tree, and it's going to be called tree.carseats, and the call will be high as a function of all variables except for sales. We're going to use the Carseats data, and we're going to use a subset, which is the training subset. And now we're going to use that to predict output on our Carseats. And we're predicting it on the test data from our Carseats, and this type equals class tells R that we're doing classification. And now we want to get a table that shows us our predictions versus the test. And so here's the output for our table. And on the diagonal is the number that we got correct of each type. So if it was called a no and we predicted it as a no, there were 140 of those, and then there were 50 yeses on the test. So if we want to measure our accuracy, it's 104 plus 50 divided by 200, and we get 0.77 accuracy. Now the R lab here suggests that the accuracy should be 0.715, but this is different than what we're getting, and I'm not sure why. I downloaded this code off the website for the course a moment ago to make sure we have the right code here, so I don't know what's different, and I've cleared my memory in R, so we're not using anything previously in memory. But we're just going to go through and show our results, and then we'll talk about what's provided with, what's the expected results in the lab. Setting the seed each time should be making sure we get the same results every time. So it's strange. I don't know why we're not getting the same results, but we're just going to go with walking through what we have here. All the commands and everything seem to be working right, except our accuracies aren't the same as what's expected. So our view and learning of the software is just fine. It just seems to be getting different output than what was expected when you set the seeds. That should be controlling the output from the random choices. Okay, so now we're going to do cross-validation. So what we're going to do, what we did up here is we split into a testing and training subsets. and we used the full tree that was trained on the training data for this prediction. We're going to do cross-validation to optimize the tree or to prune the tree. You optimize a tree classifier by pruning it. And so that's what this command does. This command creates what we're going to call CV Carseats, cross-validation Carseats, and you create it with this CV tree command, and it takes this tree.carseats, that's the tree that we made previously on the training data, and our function for pruning is going to be misclassification. So that's what this part here does in the command. And now we can look at the names that come with cv.carseats. So there's 4 different variables that are output here. Size of the tree, there's a deviation, which since we used prune misclass as the function, this deviation is actually your accuracy. K is corresponds to alpha in the pruning parameter, and method just tells us the method. So we can look at the information that comes in the CV Carseats. So this corresponds to the size of our different trees during the pruning process. So we started with a full tree of size 21, went to 19, 14, 9, 8, and so on down. The deviation went from 74, 76, 81, 81. So 74 for this tree of size 21, deviation of 76 for tree of size 19. And we say deviation here, it's the deviation variable, but it's actually the classification accuracy. And then so on as you go down the list. And then K, it corresponds to that alpha parameter that we use. It controls how much impact the size of the tree has on the training process. And so negative infinity is no impact, and then 0, and then as the impact or the amount of penalty corresponds to the size of the tree increases, we end up with smaller trees, and we use cross-validation to pick the best tree. So we're going to pick the best accuracy tree. So let's get a plot. So we're going to create 2 plots here. This plot on the x-axis is the tree size. So size, it was 1, 2, 3, 5, 8, 9, and 9 is here, and then so on. And on the vertical axis is the accuracy. It's in the dev or deviance variable, but it's actually accuracy. Here we have the Carseat K, that's like that alpha, that's a training parameter, and then accuracy is on this axis. So now we're going to, looking at these plots, we can say the tree of size 9 seemed to be a top performer here. It has close to maximum accuracy. There's actually a tree of size 2 that has higher accuracy. We'll take a look at that, but we're going to look at the tree of size 9 first. So look at the tree of size 9. So here's our tree, and just to check that this has size 9, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes, and this best equals 9 tells us we want to make this the tree of size 9, and then we're going to add the labels. And so there's our labels. And we can see just looking at this tree, it's now more interpretable than the other larger tree. Price less than 96.5, that seemed to have a big impact. Everything with a price less than 96.5 was a top seller. So that's an interesting piece of inference. And now we're going to do a prediction. We're going to use this prune Carseats, which is the pruned tree we made up here, the one we're looking at. We're going to do a prediction on the Carseats.test data, and type is class. And so Carseats.test, that we created up here. Remember, that was Carseats on everything that's not in the training data rows, and then all observations. So we're predicting with this pruned tree on our Carseats.test data. And so this is our accuracy table, and the number we got correct is 97 plus 58 over 200. So a 77.5% accuracy. just for completeness, the original expectation here would be to get a 0.77 accuracy. We get a 0.775 accuracy. .775 slightly better than 0.77, so pruning's helped us a tiny amount. The expected amount from the lab as it's set up would have gotten 0.77, so 77%, which is a little more than slightly better than the 71.715% that was with the lab result before. Okay, so let's look at this larger tree, best equals 15. We do the same thing, plot that one, so you can see that that's a larger tree. And this isn't pruned as much. It's not one of the optimal trees or one of the ones that gave great results. And so the expected error here was 0.74, which tells a nice story that this partially pruned tree does better than the full tree, but not as good as the lower pruned tree. But in the results we get here, it's 102 plus 53. Which is a 0.775 accuracy, which is as good as we got with the further pruned tree. So what we've seen here is, let's do one more. Let's look at the tree with 2 nodes. Remember when we looked at those plots? Let's prune this tree.carseats down to the tree with 2 nodes. See what happens. There's a tree with 2 nodes. This is size of the tree, 2 nodes. There was one that got a higher accuracy on the training data. Now we don't expect that to do well. Let's take a look at that tree. There's the tree. All it does is check whether that price is bigger or less than 96.5. We can predict. And then this is our results. So our results are 104 plus 27 correct out of the 200. And we get a 0.655. So this is what you would expect just thinking about a tree with 2 nodes. It's going to be a low accuracy. On our cross-validation steps, it was suggested that this was going to be a good performing tree, but the cross-validation is separate than the holdout or the training data. And so the training data is really going to give us a lot of information on what to use. It's how well does that generalize, right? So that 2-node tree worked well on what happened to be in our training data, but it didn't generalize well to our holdout or our test data. So really, the 9 or the 14 size tree would have been good, 9 or 15. Both of those would have been good. Thank you very much for watching.